¿Qué tal? Buenas tardes, sean todos bienvenidos a otra más de nuestras pláticas con el 65 aniversario de la DES de Ciencias. En esta ocasión estamos presentando al doctor Orlando Guzmán López, quien trabaja en el Departamento de Física de la UNAM de Iztapalapa desde el 2006. Al terminar una estancia postdoctoral en el Departamento de Ingeniería Química y Biológica de la Universidad de Wisconsin-Madison. En el 2018 concluyó su estancia sabática más reciente en el Instituto de Ingeniería Molecular de la Universidad de Chicago. Es miembro del Sistema Nacional de Investigadores, de la Academia Mexicana de Ciencias y de la American Physical Society, de la American Mathematical Society. En la actualidad, sus intereses de investigación incluyen la dinámica de la interacción del ácido ribonucleico y la proteína GAG para el autoensamble del virus de inmunodeficiencia humana VIH-1, el autoensamble de nanopartículas guiadas por cristales líquidos y autoensamble dirigido de monocristales y fronteras de grano en fases azules. El diseño de materia activa. Bueno, ya sin más preámbulo, le damos la bienvenida al doctor Orlando para que nos presente la ponencia que nos tiene preparada.
Muchas gracias por la invitación. Quiero agradecer a todos los organizadores poder participar en esta celebración de la DES de Ciencias. Deseo que tengan muchos motivos para celebrar a lo largo de muchas décadas también en el futuro. Entonces, mi tema de la presentación es la física computacional. Me pidieron que hablara inglés, entonces voy a pasarme ese idioma, pero si hace falta puedo regresarme al español. So, this talk is about computational physics from atoms to materials. What is its purpose? What are the means that are necessary to do such work? And what methods we use to perform such activities. And the outline of my talk will be this one. Sorry, I want to present first my collaborators because always I mess up with the last slide, so I tend to put it in the beginning. So this work, of course, was done in collaboration with many persons, particularly Doctors Linda Hertz, Sayantani Ghosh, and Dr. Moyatsin, as well as Robin Brunsma, Julia Rusina, and Paola Mendoza, as well as many other students that they will appear in the presentation later on. So the outline for this talk is this. I would like to present first imaginary talk between Enrico Fermi and Richard Hamming, two very notorious scientists which held very specific opinions about how to conduct science and what's the purpose. And then I will discuss what it means to have numbers and or intuition in the context of two problems that I've been involved in researching. And then I will give my conclusions. So here are these two giants of science. The first one is Enrico Fermi. Once Enrico Fermi was talking with Freeman Dyson. Dyson had gone to his office to discuss a new theory that he had. And after presenting it at length, and Fermi listened to it very carefully, Dyson asked Fermi what he thought about the theory. And this is what Fermi said. He said, look, in science, there are two main ways to proceed. The first one, the one that I prefer to do, is to have a clear intuition about your problem. And of course, the second one is to have instead a complete, detailed, and consistent mathematical description of it. You have neither. So Freeman Dyson was a little bit discouraged by what Fermi had said, but it turned in the end that he was right, that what he proposed was simply not true. But Freeman Dyson had a very good mind, so he was very creative and had many, many good ideas, and also had many, many bad ideas in the process. And so I think that if Fermi had a chance to talk with Richard Hamming, maybe Richard Hamming will concur, and he will say something like this, which is one quote, one of his books on numerical analysis. And he said, the purpose of computation is insight, not numbers. So that's something that happens with us in computer simulations and computer methods. We necessarily deal with numbers, but in fact, we're not so much interested in the numbers as much as in gaining insight on the problems that we are interested in. So I will say that these fellows live at the frontiers where the computers were being born and the technology that we have in the 21st century was only very incipient, nascent, but still they had a very, very great capacity for doing science. So I wonder if what they said before, that there are at least two main ways to proceed in science, and the purpose of doing computations is getting inside the numbers, is something that we could use today. And of course, there are many other instances we need to deal with math or intuition. One of them, something that you are probably very well aware of, is thermodynamics. Thermodynamics is a very, very complete science, very complete, mathematically developed, and it's built on a set of axioms or experimental information that's very simple. And out of it, you can construct any number of mathematical properties and physical quantities that if you go out into the experiment, you turn out to be correct. So here I'm giving you some examples of an isolated system, which the second law says that if there is a spontaneous transformation in it, that you remove one internal constraint in the system, what will happen is that the entropy will never decrease. And the equilibrium state that you observe in the end will be the one that maximizes the entropy. Out of that statement, and conservation of energy and conservation of mass and these kind of things, you can understand a lot of process. So for instance, here is a diagram that models a Carnot cycle that is a trajectory in the space of pressure and molar volume, where you can see that work is done. And of course, this is applicable in many instances, not only in situations where we have, say, an internal combustion engine, but also something about the ambient. So the diagram in the right is a diagram that meteorologists use in order to understand the conditions in the upper atmosphere. So when they do soundings and they send the radio sondes to get information regarding the pressure, the temperature, and so on, they construct these kind of thermodynamic diagrams and they perform calculations to inform what is the level of sterility in the atmosphere. So they are doing a lot of math. They are developing a lot of math for doing that. But in that case, is it the case that we rely more on the math than intuition when we're doing thermodynamics? Because thermodynamics turns out to be a phenomenological theory. It's not necessarily a microscope-based theory. It can stand on its axiom. Contrast, we also have statistical mechanics, which is built on the shoulders of people such as rendition, somebody that liked very much Guzman and his work, this sculpture, and his famous equation relating the entropy with the number of microscopic states that are consistent with the case. One can argue that the complex than the one that you have to do when you're doing thermodynamics, the level of understanding that you achieve is greater. So it's, in this case, statistical mechanics with all the ensembles, with all of the partition functions, with all of the ergodic theorems and so on, give to the table a lot of new math, but also bring more intuition. And sometimes if you are a person starting with subjects, you are a little bit confused about what is intuition and what is math. And I will argue that what you need is some experience, and the experience will give you the way to form intuition out of the math. And at the same time, if you have some intuition, then you can deal with the math in a very good way. So it's an example of computer simulation, the subject for this talk, where you can see that unavoidably, if you want to perform computer simulation, you must be aware that you are dealing with the numbers in the memory and registers of the computer representing numbers, and you are playing with them in a very sophisticated way in order to reproduce some behavior that laws of physics and chemistry that you're playing with will tell you that what's going to happen. to this constellation of atoms and molecules. So here's an example, one of the papers that you can get from molecular physics on the many journals in the field, where you do that explicitly. This is a simulation where we have a simple set of molecules that is a trimer, and this trimer can vary in its structure and the energy and the sizes of the molecules. Some of those can be of one potential spheres, maybe the others are Lennard-Joneses, or some of the others are square wells. And by changing a little bit of those properties, we can get many different types of behavior. So for instance, if you play with the one that is in the upper right corner, you make some computer simulation, there's some set of temperature and pressures you observe that is they are possible in these regular structures. And if you do this with another set of parameters, then you just get a blob of regular liquid rules that these molecules interact. You can construct these sophisticated arrangements of chains that resemble something like a polymer and doing crazy stuff inside it. So I will argue that computer simulations, we are fortunate to have computer simulations, because out of the simulated experience that we compute in our machines, in our hardware, we can develop intuition about the systems that we are interested in. So in order to bring my point to a clearer focus, I want to talk about two examples of my research. One is a problem about nanoparticle self-assembly that is guided by a liquid crystal, and the second one is about the structure and function of one of the proteins of the HIV-1, the virus that causes AIDS, and the GAG protein that is the structural element of its capsid, its packaging capsule. So for the first one, I was involved in this because one of my a couple of my collaborators, in some experiments, and the experiments involved some nanoparticles that were coated with some mesogens, some particles that are elongated and were able to create a liquid crystal. And they decided they wanted to disperse these colloids inside the isotopic phase of 5Cb. 5Cb is a methyl cyanovinyl, which is a very common liquid crystal for research purposes. So they said, we want to engineer these particles so that the 5Cb doesn't really see the nanoparticles. They will see the code, and they will go inside of the 5Cb, and it will be well suspended. So they were very successful in doing this, and they were able to make homogeneous dispersion of these coated nanoparticles in isotopic 5Cb. But they had a problem. And the problem was that when they changed the temperature and brought the 5Cb into the nematic phase, they saw that there was precipitation. These homogeneous dispersions were no longer stable, and the nanoparticles tended to clump together and create structures. This is what they saw in one of their experiments. For these experiments, we are looking at a microscopic image, a movie, and there are two components. One of the components is a fluorescent nanoparticle, so that whenever there is a clear field, you are seeing the light that is coming from the fluorescent nanoparticles. And on the other hand, there is 5Cb. And 5Cb is seen between cross polars, two axes. It will be extinction of the light, and you will see a dark field. So this is what they saw. When they change the temperature very quickly, and they go through the phase transition, they observe the creation of structures. So the particles tend to clump together, by 10 microns, depending on experimental conditions. So it was a kind of a puzzle. You have some fluid that is homogeneous, you bring it through the phase transition, and you end up with the same fluid that is inside these microshells made of nanoparticles, and the same fluid is outside, and they're in the same phase. Both of them are nematic. How is that happening? So at the moment that we discussed this, we didn't understand the problem, but we thought that maybe we could do some modeling, some intuition to the table, or we could do some numerical simulation, we could figure it out what was going on. And this is a cartoon of what we thought was happening. This is what Linda and Sai told me that they thought that was happening. And they say, look, the thing that must be happening is that the nanoparticles don't like to be in the kinematics. Therefore, they clump together into some domains. Those domains, the liquid crystals in the isotopic phase realizes that different nanoparticles from the interior, and they end up between a rock and a hard place. Essentially, they get pushed to the interface between the two domains, one inside, one outside, and that's what you get the micro shells. And we said, well, that sounds like a very good explanation, but can we support it maybe with some calculations? And this was the work of one of the students that was a graduate student then, and he came up with this model. He said, we can make a model where we have a spherical cavity, very simple geometry, and then we decide that there is another spherical cavity inside, and that is completely pneumatic. And then we make some thermodynamics. We can write expressions for the free energy of the nanoparticles that are floating in the isotopic phase. He said, I know about the theory of liquids. I'm going to use the Carnot and Starling excluded volume particles for dealing with that. And for the other part, I'm going to use standard elastic energy and phase transition, Landau-Degen, free energy expressions for that. And he said, that's maybe all it. And he said, but the problem is the equations are non-linear and we have complications about the profile, so it's better we do a simulation. And what he proposed was to do some Monte Carlo simulation, but instead of doing Monte Carlo simulations with molecules, he said, look, this liquid crystal is described by a tensor of the parameter. The tensor of the parameter measures with this S the degree of alignment. And also with this director N, it says in which direction you are. And if you combine them into a tensor, you have a unified description of a liquid crystal where even you can describe topological defects. So that's what we're gonna do. And so armed with that and a computer, he devised how to do Monte Carlo, Metropolis Monte Carlo rules for doing simulation. Essentially, what he does is that he changes a little bit the elements of the tensor and only accepts them either because the free energy decreases or because there is some probability given by the Metropolis rules that allow him to go a little bit in energy with the correct expectation in the end that will leave him in the equilibrium. Sees that over many Monte Carlo steps, the free energy of the interior droplet of pneumatic is minimized. And when he does that, then he has his answer. He has what is the structure of the liquid crystal. In this movie, what we are seeing is the order parameter. And eventually what he sees is a sphere region that is a topological defect in the center of the sphere. And there is of order that goes to the surface of the sphere, and do this for many sizes. He performed this kind of simulations with many different diameters. The diameters correspond here to different colors. Red is a small radius droplet, blue is a larger one, and green is a larger one. And when he was looking at these results, we realized this is interesting. What we're saying is that if the droplet is long enough, say the red one or blue one, then the profile that is inside is really not depending on what's doing the liquid crystal away from it. And so we said, okay, that sounds interesting. That simplifies the problem. And he came up with a way to approximate the profile. He said, this looks like a Gaussian. And he suggested using a Gaussian to represent the profile, adjusted it, and because it was a Gaussian, he was able to integrate everything because Gaussians are very simple to integrate. And so because of that insight, the structure of the inner defect is mostly independent of what's doing the liquid crystal droplet very far away from it. We got an analytical answer that he could use to solve the problem. So he got all the free energies that he wanted, and he created a model. And the model essentially said that if you have a droplet of a given radius, the free energy can have two types of behaviors. One, if the temperature is very close to the transition temperature of the isotropic nematic phase transition, you will see that the free energy is monotonic, and its minimum is 0. That says, look, the first thing that you can do is look no droplet inside your regions, and you will see no formation of microshells. But he found that there was another transition. If you decrease sufficiently the temperature, then there's another minimum in the free energy develops. And this corresponds to a droplet of liquid crystal inside the sea of nanoparticles that has a definite radius. And this corresponds to the structure that we see as microshells. So in this case, what I want to stress is that out of some intuition, a model was built, a numerical model, and it was also performed numerically with a sophisticated treatment, if you want. It was very, very time-consuming at the moment with computers that we had at hand, but what we obtained in the end was a very clear physical picture. What Noé said is, in the end, there's only just two components. One, the nanoparticles don't like to get pushed. If you push them a lot, the free energy is going to get up. And the other one is the liquid crystals really want to change the phase from isotropic to the nematic phase. Why? Because then there will be some latent heat release. And it's the competition between that rise to these curves. So there must be some equilibrium. And when that equilibrium is reached, a microshell is born. So sometimes when you reach that kind of insight, you get greedy. And you say, maybe a little bit more. And that's what happened, because Noé to suppose that it was absolutely impossible to have one of the particles inside the nematic phase. But that's probably an exaggeration. So the way you have to change that and to make it something that is more physical, perhaps, is to say, well, look, if we look at the free energies that come from nanoparticles and come from the liquid crystals, this is the non-conserved field parameter, that is the liquid crystal of the parameter, and this is concentration of particles, there might be some coupling into it. So there is some contribution to the free energy that the level something very, very simple as this, like a polynomial, a lambda of the Gn expansion. At that level, there must be some coupling. And the kind of symmetries that allow you to include some terms, but not others, in the free energy of the liquid crystal also tell you how to include the terms in this coupling term. So we did that. We said, okay, this is the free energy, and we are going to paint the dynamical equations from it. And these dynamical equations turn out to be partial differential equations that are nonlinear, and we didn't know how to solve. So what do? Well, when you do that, then you say, well, we should go to the other way. This coupling represents something of interaction between nanoparticles and liquid crystal. What is that? And so in another situation, Emmanuel Flores made simulations, molecular dynamics of rods, and what he simulated was what happens when you change temperature. So he's had these mixtures of rod and nanoparticles, and he makes simulations at ever colder temperatures, and he sees a transition in the order parameter. He sees that the order parameter suddenly increases, and that's transition. But what's interesting is that temperature of transition increases with the concentration of the nanoparticles. And if you look at the equations with the concentration of the spheres, and moreover, the slope of that reduction in the temperature of transition is a measure of the coupling constant. So what we did for is to assume that the coupling constant was just a number. And here we have evidence that, well, it's not really a constant, it's a coupling parameter. And that parameter is small for small pressure, but increases very quickly with the pressure. So if we do simulations and we do experiments at 1 atmosphere, and we repeat those experiments at 10 atmospheres, what we'll expect is that even more difficult to insert nanoparticles into the nematic phase. it will be much more difficult for the particles to remain well dispersed in the liquid crystal. That's something that has to be tested. For the moment, it's just a prediction from simulations. Well, sometimes you have to go back to pen and pencil, pencil and paper. And for that, what you do is you have a bunch of hairy equations on all of that. And what you can do is that you can make a linear stability analysis. And what's that? Well, you make connections bounds, control the growth rates of perturbations. You have to do this in Fourier space. It's easier. And for doing that, you have to have the spatial frequency, the reciprocal wavelength of these perturbations. And then you can realize that a positive real part of the eigenvalues is that these perturbations will grow exponentially.
Retomamos su conexión, doctor Orlando. Ya lo tengo otra vez con los permisos asignados. Si nos hace favor.
Okay, thanks. Sorry about that. There was some problem with my connection. I will try to recover what I was doing before. And I was saying that sometimes when you're dealing with complicated instability analysis, try to expand around some stationary states and see what's the fate of fluctuations, small fluctuations around it. And in that way, you can identify, in this case, that the long wavelength perturbations to a uniform background can increase exponentially in time under some conditions. And these conditions involve, in our case, temperature, concentration of nanoparticles, and the wavelength of these perturbations. And this analysis tells you that it's the long wavelength perturbation that gives rise to instability, to the unstable modes. And that's something that we wanted to check. And once again, we came to the numerical solutions. And for doing that, you restore the nonlinear terms into the equations and rely on a numerical solution of the partial differential equations to obtain the behavior in time. And we have done this in 2D and 3D. And essentially what we observe is that 3D behaves exactly as the thing that you see in 2D. So there is a little advantage of doing the analysis in 3D if you can obtain equivalent information from the eigenvalues and the linear stability analysis and the simulation of 2D systems because they are cheaper to perform in a computer. So with that, I want to change gears. I want to say that sometimes when you go into some problem and you develop some methods to it, you will be interested in applying those methods to other problems. And sometimes you just happen to see another problem and do not recognize that maybe the same thing. So it happened that while we were doing all this self-assembly, we were contacted by other colleagues that were interested into the assembly dynamics of GAC proteins, of the human immunodeficiency virus, the virus that is responsible for AIDS. And the thing is that this kind of virus has a kind of protein, a protein that is about 500 amino acids long, that is a modular structure. It has many domains. This protein GAC And this is a cartoon of what GAC does when it attaches to the membrane of an infected cell. It starts to grow and eventually creates a capsid that is separated from the cell. This is called the immature virus before some enzymes act locally in GAC and cut it so that there is a mature form of the virus. What I'm going to discuss is about the immature virus. In the immature virus, there are many participants. The protein has many components. There's the MA regarding the matrix, the thing that associates with the plasma membrane of the cells. This is the CA protein, which has two domains, the NTD and CTD domains, and these are responsible for creating the capsid of the capsid of the virus. There is another thing that is called the nucleocapsid. That is the part that is released by the action of enzymes, and that's associated with the genome of the HIV virus. But before that happens, it's basically a sphere. The immature capsid is basically a sphere about 120 nanometers in diameter. And we were interested in some reports that say that while the GAC protein is extended in the immature virus, when it's in solution, it's twisted and it's in a compact form. And the evidence was coming from experiments doing some FET, Foster resonance energy transfer, that says which parts of the molecule are close together, and also for implicit solvent simulations where you use that imitate the behavior of the components of the protein in the absence of the water, because that's so much faster to do. And so both of those evidences said that there were parts of GAC that were touching each other when they cannot touch if they are completely elongated. And we wanted to know what was going on. So what was suggested from this analysis of correlation of which parts of GAC were interacting with each other were that some of the MA domains were interacting with the CA domain. And we wanted to check that. And that's what we did. In this case, we decided that we really wanted to put the water inside. So even if this movie is not showing the waters that are in the simulation, we did this with three different types of waters, because even if the technology for simulating biomolecules has improved a lot, there remains some uncertainty of which force fields are adequate for representing proteins, which forces are adequate for representing RNAs, which force fields are compatible with some of these potentials for the biomolecules. And so we decided, well, look, if we're going to say that this part of the molecule of the protein is interacting with each other, better if this does not depend on the model. So we decided to go all in and try many different types of potentials. And it turned out that we could identify one particular configuration between MA and CA, the domains of the GAC protein, that remain associated even if you change the model of water that you use. So what we did then is that we wanted to characterize the strength of this. And one way to do it, if you're a physicist, is to try to evaluate what is the potential of mean force. What is the free energy associated with moving these particles away from each other? So this is what this is showing. We perform umbrella simulations where one of the molecules fixed at one place, and you allow the other one to fluctuate in a harmonic trap. And because of the harmonic trap, this go away and keep samples, but it does so in the presence of the potential of mean force. So you know that you added a fictitious force, the harmonic trap, and you're trying to investigate to figure it out. What was the force that was there in the potential of gravitational will go to a new equilibrium. If you can measure the equilibrium and make histograms around it, you can figure that's what you do. You collect a lot of histograms. There are technical details for ensuring the histograms can be compatibilized. And if you do that, you discover the potential of mean force. And that's something that a physicist can appreciate. If you look in between 2.2 nanometers of distance and say something like 2.8 nanometers of distance, there is a constant force that's pulling this. There is something that's really just trying to catch we can characterize this and give the numbers to other physicists. They say well, it's 6.8 kilocalories per mole, and they say, "Oh, that's something." And so that was interesting to obtain from all these numerical evaluations to get a physical picture of what's going on. And the physical picture is this. This is like the two-level system that is constrained, subject to a constant force between these two levels. And if you do that, you obtain this curve, and this curve can be fit to the numerical simulations that you obtain. So, of course, we've been doing other things with the virus assembly, but I don't have the time to discuss it right now. And so I want to conclude with this. In our field, it's very easy to get interested in the numerical methods. It's very easy to try to solve the same problem with a new and advanced methodology. It's probably something that we want to do because we really enjoy playing with the computers, but we also want to know about the systems, the physical system that we investigate. So you find useful that I remember Richard Hamming when he said that all the purpose of what you're doing is not the numbers. You're looking for some insight. And I also think that you think about what Fermi said to Freeman Dyson, that either you have a very clear intuition about your problem, or you have a very complete, consistent mathematical description if you're lucky. Hopefully, in the process of doing this, you will have both. And thank you very much, and I'll try to answer your questions.
Thank you very much, Orlando, for this talk. I think that it's really useful for the students that are watching at this conference by the YouTube channel. So, okay, let me see if there are questions from the audience. Abelardo, Magdalena, or from the, yeah, I have, yeah. One of the students was asking about the machine learning algorithms in this kind of soft material system that you are studying. They ask if you implement this kind of algorithms in these methods, computational methods that you use.
Well, that's a funny story because while we were doing all of these calculations of the topological defects and so on, we wanted to measure their behavior. And the easiest thing to do is to bring a machine learning algorithm to try and do the classification. But for the particular thing that we're doing, we needed to train the machine learning algorithm, and we needed to explicitly tell it which of these were positive topological defects and which were negative topological defects. And from the pictures on the right, on these black and white things, you cannot really show it. But if you go into the left ones that show you the angle of the liquid crystals, then you can do it very easily. You just have to look at the colors and how they turn from one to the other side. So when we're doing that, the student that was doing the project said, "Oh, that's what you mean when that's a topological of positive sign and that's a negative sign." So in the process of teaching the computer what a topological defect is, he figured out for himself what a topological defect was. So it's a good thing to have machine learning, but in the end, at least with the method that we were using, it depends so much more on the intelligence of the student doing this. So I was very lucky to have a very bright student that they said, "Oh, look, that's what I have to tell the machine."
Definitely. Yes, of course. All right. So we don't have more questions from the audience. Let me see. No, it seemed that that was the only one. So I know that you are in a hurry, Orlando, but thank you very much. I really appreciate your talk and the time that you gave us for this event of the 60 years anniversary of the physics in San Luis Potosí. I really appreciate.
I just want to repeat.
All right.
I just want to repeat that I'm very, very thankful for the invitation, and my best wishes for celebrations and that you have a lot more successes over the next decades, and very happy to participate somehow.
Thank you, Orlando. Thank you very much. Have a great day. Have a great weekend, and I can send you a virtual applause for this talk. And thank you very much for your time.
Thank you very much. See you.